Okay, here we go. This is the array that we're going to try to work on. Go ahead and sketch this one out. Electron, proton, electron, proton, proton. And we're going to try to figure out the interaction forces, and then from that get a net force on one of the charges, because what we want to do is figure out where the electrons go. If we were a solar physicist, we would also want to figure out where the protons go. But for us guys, we'll just stick for the electron today. So we're going to try to get a net force on one of the charges. And then the net force will tell us the accelerations and eventually where that electron is going to go. So go ahead and construct your diagram. And it's going to be on the bottom of the next slide and the next few slides. So let's keep going. All right, first assumption. Let's say that these 5 charges are equally spaced. Now this is kind of an idealized view of a molecule, but it's kosher. This is kind of like a proton. This is kind of like a hydrogen and a helium. 2 protons in a helium, 1 proton in a hydrogen. So it's kind of simplified. So what that means is the distance between the 2 electrons is double the base distance. All right? The base distance between the left electron and the first proton. Okay, so that base distance from the leftmost electron to that first proton, that's my nearest neighbor distance. Go ahead and write that phrase down, nearest neighbor distance. And that second electron is double that. Right, and so on. So you can figure out all your distances. If they're all equally spaced, then the interaction forces will all be figure out. You can figure out all the interaction forces based on this one interaction here between the nearest neighbors. Because this second neighbor out, if you're focused on that leftmost electron, the second neighbor out right here is going to have an interaction 1/4 the size. This one, 1/9 the size. This one, 4 times as far, 1/16 the size. So if you know the nearest neighbor interaction, you got all the other ones as well, if you do a little bit of algebra. And you got to keep track of pluses and minuses, stuff like that. So anyways, let's keep going. So the leftmost electron gets the smallest pull from the rightmost proton. All right, so this guy over here, our target particle, it's being attracted to that red proton at the end. But it's not very strong. It's getting a little bit of pull, but he's all there 4 times as far away as the nearest neighbor. So the nearest neighbor is dominating. But he's still contributing, so you got to add that in. You got to figure out, what his contribution to the net force is. Okay, so the biggest pull to the right on that target electron is, as a matter of fact, put a little star or something over here by this electron. This is our target particle, or question mark or something like that. Okay, so this proton over here, this is the nearest neighbor. And so he's going to have the biggest pull, whatever it is. And this guy over here is going to have 1/16 of that. Right? So all the interactions together comprise the net force on that leftmost electron. Now you're going to have homework over the weekend, and you're going to have a problem on the exam. I'll just tell you right now, you're going to have this problem, something like this. It might not be this exact arrangement of protons and electrons, but you're going to have a brain burner on the exam. Exam 3, everybody's going to see it. It might be in the multiple choice, it might be in the clicking, but you're going to see it. So get ready to work. So our strategy is basically this. Okay, so go ahead and make a careful sketch of this diagram. Knowledge of the nearest neighbor force and the distance ratios. 2 to 1, 3 to 1, 4 to 1. 74.6 to 1, whatever it happens to be, allow you to figure out the net force on any of the particles. And I mean any of the particles, not just the leftmost one. If I was to choose one in the middle, you could do that as well. A little tougher, but you could do it. And that's because, in general, the Coulomb interaction is a 1 over r squared force. All right, so let's work out this strategy, pair by pair. And also make a note here, work pair by pair with your target particle and one of its neighbors. Then form another pair, target particle and another one of its neighbors. Okay, and then just do the pairwise interactions and then add them all up. And you can figure out the net force. All right, here we go. Now, first thing that you've got to know, the nearest neighbor interaction. So let's say that for this array, the distances are such that proton to electron, nearest neighbor, right in here, the leftmost electron and that next proton is 288 nanonewtons. All right? So that means that the electron's getting some rightward 288 nanonewtons, and the proton is getting leftward 288 nanonewtons. All right? So because of Newton's third law, equal interactions. Okay, so we got plus or minus 288, but the one that we're focusing on is the electron. So first of all, we have that 288 nanonewton interaction. All right, now that is our toehold. If we can get that, we can get everything else. All right, if they're equally spaced, or if we know the distance ratios. You know the distance ratios and the nearest neighbor force, bing, you got it all. If you do a little bit of algebra, that's what we're going to do right now. All right, so let me move this up. And so we've got a positive 288 newtons to the right for the first interaction. Now the next one is the second neighbor out, and he's twice the nearest neighbor distance. So this electron to electron, oh wait a minute. Do electrons attract or repel? Two electrons. They repel, right, because they're both negatory, all right? So we have electron to electron repulsion, and it's 1/4 of the nearest neighbor interaction. All right? So now you know how big it is, but what direction is it? All right? Well, it's going to be repulsion, so it's going to be our target particle's this guy, and it's going to be repelled away, so that means leftward. All right? So we're going to have some negative nanonewtons of repulsion. All right, so let's just make a list of what we got here, okay? So here's the first one, baseline nearest neighbor, okay? Rightward 288. And then here's the one we just figured out. The second neighbor interaction, 72, and it's negative because it's pushing my leftmost electron off to the left. It's trying to repel. All right? So there's the first two forces. So we got both of these guys squared away. All right? And we're still working with the nearest neighbor interaction force. But now let's get the pull force from the second proton. In other words, let's get this baby. Okay, that second proton is going to be pulling the electron off to the right. All right, now it's not going to be 288 because he's, let's see, 1, 2, 3 times as far away. All right, so here we go. 3 times the nearest neighbor distance. And so that means, let's see, 288 divided by 9. What's 288 divided by 9? 32? 270 plus 8? Yeah, okay. All right. All right, so let's go back to our little diagram and figure out what we... Oh, first question. Go ahead. Yeah, it's the distance ratio. The distance ratio is 3 to 1. So you square that and then you go 1 over that, okay? And that's always the shrink down factor, okay? And then you can decide if it's left or right, and negative or positive. And, so it's every decision that you make is not that bodacious, but you got to make them, a lot of them, and they have to be in the right order, and it's easy to mess up. So you got to do it carefully. All right. So let's stack them up. Okay, so this next force, 288 times the 9th, 32, and it's pulling my target particle to the right, so it's positive. All right, there it is. And hey, you guys, you're going to be doing one of these in just a minute. I'm going to kind of walk you through, and then I'm going to turn you loose at the end to figure out the final answer. All right, so we got 288 plus 32 minus 72. All right, so that's good. So there's your third neighbor attraction force. You know, when I'm doing this on pencil and paper, I write down 3NF, third neighbor force. It's pretty compact. Pretty cinchy way of expressing it. So, okay, we're squared away on these 3 babies. And those 3 guys form a pair with the target particle. Question all the way in the back. The question is, where did 72 come from? It came from this interaction. My target with this middle electron. The middle electron is trying to push this baby off to the left. And this baby over here is trying to push this middle electron off to the right. Now, we're trying to figure out the net effect on this leftmost baby. All right? So I take my nearest neighbor interaction, 288, and this guy is twice as far away, so distance ratio is 2 to 1. Square that, 4 to 1. Flip-flop it, 1 to 4. And so, you follow me? 1/4 times 288. Okay. And it's negative because it's leftward. Okay, so that's the last thing you got to decide. All right, so let's keep going. We have one more neighbor, one more nosy neighbor, the one furthest down the street. All right, so that's this guy way out here, the third proton out. Now, it's going to be a rightward pull force, so I'm going to get a positive, but it's going to be kind of pokey. All right? So now, this is 4 times the baseline distance. Okay, so young lady in the back, what's your first name? Yeah. Sadie. Distance ratio is 14. Shrink down ratio is 1/4 squared, or 1/16. So let's see, 288 divided by 16. That's got to be 18. Okay. Okay, so there's the weakness factor, or the shrink down factor, 1/16. All right, so 288 by 1/16 is 18. And okay, here it is. They're getting kind of teeny. And basically, you know, the interesting thing is, if you're thinking about one of the particles on the left, the nearest neighbors, and if they're equally spaced, the nearest neighbor always dominates. So the nearest neighbor is never going to be, even if you have all electrons out here, the nearest neighbor is never going to be outdone by anything you space out equally off to the right of it. Okay, this won't happen. It doesn't work out mathematically. And in this case, we have a couple protons out there, but they're not adding a whole lot. But even if we had electrons out there, they wouldn't overwhelm that 288. So no matter how many you had out there. So here's the fourth neighbor attraction force. And we've got them all squared away now. And you could just add them up. 288 plus 32 plus 18 minus 72. And that adds up to 266. All right? And so your net force, it's not as long as the nearest neighbor force, but it is in the same direction. It's 266 newtons. All right, now let me pause for questions, because you're going to work out some of these, and I see questions in the back. Go ahead. The 1/9 was for this guy, because he's 3 jumps. Think of it as like checkers, 3 jumps away. 1, 2, 3 jumps over to the target particle. So that interaction distance is 3 times the size of the nearest neighbor interaction distance. Okay, so 3 to 1, square it, 9, flip-flop it, 1/9, and that's your shrink down. Okay. Jacob. Jacob's asking me, is 288 just a random number that you threw at us? Kind of. I wanted to make sure it was something divisible by 16 and also by 9. But it'll change, yeah. If I give you 107, you're going to come up with fractions, decimals and stuff, but same philosophy. I just wanted one that you always get an even whole number. But if you have, 88.9, you could do everything the same way: 1/4, 1/9, 1/16, 1/25, and on, and just add them up carefully. Same thing, just a little bit of fractions and stuff. That's all. Question over here. Yeah. The question was, on the exam, will they be equally spaced? The answer to that is yes. On the homework, they'll be equally spaced. The homework, let me give you some advice, some mental advice. I yelled at a bunch of guys over here for blabbing, but over the weekend, I want you to blab as much as you possibly can in discussions. Okay, let that be because this is going to burn many brains. But if you keep working on it together and stuff, and Darian and Nisha, are you in the system yet? Nisha's supposed to be. Anyways, I'll be in the system over the weekend, and Darian will be in there, and Shai might be able to chip in a few nuggets of wisdom, and we'll just get through it together. All right, because you're going to be It'll feel good when you get them every time. So, another question. How many special study group leaders are here? Raise your hand if I invited you to be a special. 1, 2, 3 in the back. 4. At least, see, now this is a problem. The special study group leaders aren't here. There's about 12 of them. Maybe I should withdraw the invitation for those slackers. All right, let's go and work it out step by step. Here we go. You ready? Okay, here's our array. Slightly different, but equally spaced. And now we're going to calculate the net electric force on the leftmost electron again. I could just as easily ask you the rightmost proton, though. That would be, something interesting. But let's do the leftmost electron. Different array. Write it carefully. And when you're doing your homework, do not recycle answers. Okay, read every item carefully. All right, now the new nearest neighbor distance is a little bit smaller, so that the nearest neighbor interaction, and actually this is the interaction between any nearest neighbors. If they're all equally spaced, they're all either a plus or a minus of the electron charge, then any nearest neighbor interaction is going to be 576 nanonewtons. All right? Right, so this is our basic thing. So by the end of this series of questions, you're going to have an answer, and you're going to work it out. And I'm going to trot you through some multiple choice answers, multiple choice questions, and then finally a calculation question. Okay, so, and I have the same display at the bottom of the next page. Here we go. Question 2, I guess, for today. The force on the leftmost proton, of the leftmost proton on the leftmost electron. All right, now this is a simple question. Is it an attraction rightward, attraction leftward? Is it a repulsion rightward? Is it a repulsion leftward? First basic thing, and you're going to have to decide this for every single interaction pair. Good, I see people going like this, and it's good. Now you can talk. Did you see that message, Elijah? Or is he? What's your first name? Elijah. Yeah. Did you see your message? Yeah. Are you going to be a yes or a no? 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted for. Uh-oh. We got a little explaining to do here. Correct answer is A. It's an attraction rightward. Okay, this electron is attracted to this proton. The proton is to the right, therefore the attraction force on the electron is to the right. Right? Now, this proton is going to get an attraction force, but I don't really care about that for this problem. All I want to know is what this baby over here. So make sure in your diagram you put a little star or a question mark or a check mark or something next to that one. That's our target particle. All right? And that's your first decision. Okay. The force on the center electron, from the center electron on the leftmost electron is, okay, same question, but different pair, different interaction pair. So what's the leftmost electron getting? Leftwardness or rightwardness? Is it attraction or repulsion? And definitely talk it over with your neighbors. It really helps. Hannah and Danielle, where are you guys? Hannah and Danielle. Did I answer your questions that you want to about the groups and stuff? All right. "30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. You got some explaining to do. The correct answer is D. Most of you, we're still getting a little noise over here. We're still getting a little confusion. So let me explain this one again. Let's see how you guys do. All right, let me move this out of the way. Okay, if you voted for repulsion rightward, this middle electron, the center electron, and the leftmost repel. Now this is my target particle. It's going to have a repulsion away from the other particle, to the left. And that's why D is the correct answer on this. All right, let's go to the next question. And my comment is, so far we've got some leftward, and we've got some rightward, and we still have to figure out the sizes. So make a note of this. Anyways, this is kind of like, I don't know, about a fourth of the way through. You got a bunch of decisions to make. You got to calculate sizes. We haven't done that yet, but we'll get to it. And we still have to figure out force, size, and direction for these two babies out here. All right. So we got 4 neighbors. So I have NNF, nearest neighbor force, 576 nanonewtons. I got 2NF, the second neighbor force. I got 3NF, third neighbor force. And I've got 4NF, the fourth neighbor force. That's the guy out on the right side. All right, here we go. Interaction force between the leftmost electron and the rightmost proton. All right, that's the one. That's this guy out here. All right, we're going all the way out to the fourth neighbor force. How big is it? Is it an attraction? Well, it is an attraction. Electron and proton is an attraction. But which one's the right size? So let's see, how many checkers moves is it? One, 2, 3, 4. Fourth neighbor out, 4 jumps. 4 distance jumps. 30 seconds. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Dun-dun-dun-dun. Very nice. All right, for those of you, about 16% of class missed that. It's an attraction. Of course, everything here on the list is an attraction. 576 divided by 16 is 36 apparently. So there's your answer. All right. Now we're going to put it all together. Hit the refresh key and put it all together. And if you get a leftward, make sure you put a minus sign in first to indicate leftwardness. If you get a positive, go ahead and put that in, just a regular number. And let me choose numeric. All right. Hit the refresh key and then go ahead and I'm going to turn the lights on. Shy, what do you think? Easy now, huh? But yet, when you first do it, that's nervous times. It's easy when you know how. I don't know what the answer is. I didn't work it out myself. I didn't write it down. TJ, what do you got? Positive. Yeah. That's what you got? That's what I got. Good. Ooh, you must have, you have your license to operate now. What? You're both TJs? Did you both get the same answer? Got it? What did you get? Genius. I guess that must be the genius roll right there. "45 seconds. Ivana. Ivana. You guys done? Got it? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see how you guys do here. Uh-oh. I see some students that voted for 532. What? The correct answer is 404. And a lot of you guys got that. Good. But can you do it again or homework? Let's see. All right. You're not dismissed. I want to talk about the exam. Just a few minutes to get you ready for the exam. Now, let me review the procedure. For special study group signups, you'll be able to look at the schedule all the way up until 5 p.m. tomorrow. At 5 p.m., Group 1 will be allowed to sign up. Group 2, you guys, shh. Group 2 will be allowed to sign up at 7 p.m. Don't try to, I'll boot you out if you try to sign up before that. Bring your iClicker to the exam. There's a good chance that the clicking you just did, you may see it again, or some variation of it, or an even tougher one on exam 3. There'll be some bonus points. So like last time. And that's probably going to be on the clicker side of the test. Scantron clicker calculator. Very similar format. By the way, just so you know, I've asked the special study group leaders to hold their session somewhere between 9 a.m. Saturday and 10 p.m. Monday night. All right, so it might be Saturday, Sunday, or Monday sometime. And it'll be similar time during the final exam week, because we'll do another SSG to get ready for the final. All right, I'll be up here for a few minutes. You're dismissed. If you want to ask questions, come on up. Yeah.